So you want to put something that's going to vanish, so you're going to put epsilon here. Okay, so this is vanishing viscosity, means that you put the viscosity here, smoothing effect. Brownian motion. I think Nero will give you some interpretation of that in terms of Brownian motion, optimal control theory. I'm not going to do that. So we're going to look at this problem. And then we're going to look at the case that epsilon goes to 0. It's like if you look at Navier-Stokes and we vanishing the viscosity to get oil higher. Well, but it's not that fancy. This is easy. Way. But anyway. So maybe, by the way, this is just normal parabolic equation. We have hypothesis theory of this. So for example, you have epsilon exists, unique, and smooth in, that means if edge is smooth, everything is nice. Okay. So the point is that maybe when you pass the limit, this is kind of physically correct. It might converge to the physically correct solution. Okay. So if you have some converge to U in some sense, I'm going to describe some sense, then maybe U is a physically correct one. Sort of thing. Okay. So that's sort of the intent. That's sort of the idea. Okay, so for this equation, let me call it C epsilon. So the Cauchy problem with epsilon. So for C epsilon, I'm going to do this in the third lecture, a priori estimates. So we have some a priori estimate. A priori estimates by non-standard method. I'm going to do this. This is sort of standard, but I think it's useful, so I'll do it in the third lecture. That we have the bounds that there exists a universal constant, universal under some condition. To be specified later, under some condition, there is a new universal constant C greater than 0 that is independent of epsilon, such that you have the bounds that U epsilon T is bounded and du epsilon T is bounded. So U epsilon T plus du epsilon less than equal to C for all epsilon and for all S T. Okay, we have this universal bound. Well, assume that. This is easy to prove. I'm going to prove that later. Okay, so, with this bounds, and yeah, I forgot. So this is in Rm times 0 infinity, just like David. I'm lazy dealing with I'm going to do either with this or periodic. Actually, I prefer periodicity for now. That's fine. Okay. So with this, we can quote some kind of fundamental theorem in analysis, I guess. So we can use Ascoli theorem. To have that, this is sort of equicontinuous and stuff like that, in a compact set and so on and so forth. So the X is a subsequence, epsilon j goes to 0, such that we have U epsilon j xt converge to U, and the X is U, continuous, forever. Sometimes I'm counting, so let me know, but converge to U xt locally uniformly. So Ascoli theorem only works for bounded domain, but you can always extend the domain by using like diagonal addition to have this conversion uniformly in Rm on Rm plus 0 infinity. Oh, this is not a problem, but okay, we have some conversion in the locally uniformly sense. So it kind of makes sense that maybe this one is kind of a correct solution. But again, we haven't seen anything, right? We just see it kind of at the functional analysis level. We have some bounds, we have some conversion by Azela-Ascoli theorem. Okay. So here's the observation of Evans, which is sort of interesting. So the question I want to raise is that what additional properties that you have? Additional properties that you have. Because we are saying that we have some kind of physically correct procedure of approximation to what additional properties that we must have. So, well, it's not very clear, but let me back up a little bit and look at that equation. You know, I guess some of you might ask clearly that, you know, why don't we use some kind of calculus of variation or, you know, geometry stuff, get more properties. But look, this is fully nonlinear in du epsilon. There's no way that we can use integration by part and fix the hard part to the test function to get the result. There's no way. Right? So we cannot use integration by part techniques. As this integral h of x du epsilon times the test function, let's say phi, is, you know, there's no way to kick this derivative. Okay. It is hard to handle. Okay. So actually, this is kind of, I don't have time to mention this along the course, but this is sort of, instead of doing integration by parts, it's some sort of like L infinity analog of integration by part. L infinity means that because this is sort of like, we know that this is bounded in L infinity. Even though we cannot get it, but there's some kind of way to think about it. So this is some sort of L infinity analog of that. Okay, so here's the observation of Evans. Which is kind of weird if you look at that in the first time. So instead of take the test function and doing integration, I'm going to ask myself, okay, so take 3 as a test function, such that I have u minus 3 as a strict maximum at the point x0, t0. Okay. Again, this is L infinity analog, so we kind of test it in a weird way. So how does it look like? Let me draw a picture of how does it look like and how do we see it. By the way, if you have any questions, let me know. I'm sort of trying to do it the easy way, using all the orders. Some of us are tired with the one final. So it looks like this. You have u here, kind of continuous function. Okay, you're gonna touch it. You're gonna test it with something free. Let's say this is a free. This is the point x0, t0. So I assume that u minus 3 has the strict maximum at this point. Because u minus 3 is 0 here, right? U minus, you know, it can be above Phi can be above like this, but you can always lower it without giving touch. So you have u minus phi at x0, t0 is equal to 0, and u is less than, u minus phi is less than 0 otherwise. Alright, so it's kind of, it has a maximum. Okay, you don't need to have it to be equal to 0, but you can always add, subtract some constant to make it equal. So here's a picture. Okay, what happened if I were to touch, I were to test the function u by this function 3? What happened? So remember that we have u epsilon j converge uniform, locally uniformly to u. Okay? So for epsilon j, very small. So sometime I'm going to use this notation in apply math, so epsilon j very small. Less and less than 1. So it's very small. You see that u epsilon j is kind of approximately equal to u, something like that. Right? It's kind of approximately equal to u. Oscillating, but we have uniform conversion along this process. So you can see if you localize, this is an exercise for you. If you localize in this neighborhood, and for epsilon j very small, on the boundary is always greater, phi is always greater than u epsilon j. So that means we're going to have the following: u epsilon j minus phi going to have a local maximum at some point x epsilon j t epsilon j nearby in this small neighborhood. By the way, I'm free in the afternoon, so if you have some questions and stuff like that to discuss about some details, we can all talk. But like just formally, you see that this is kind of more and more close to u. So it's going to be closer and closer, and then because u minus phi has a strict maximum, this one is going to have some maximum like something like that. And by passing some subsequence,